Not really what? Oh, well, the projector's broken, unfortunately, so we're going to have to do the sans projector, but we will probably do OK, I think. All right, so today, first of all, I'm sorry we don't have the mid-year graded yet. It's actually, we're working on it, and it'll probably be done by Friday, so I'll probably do that. As I mentioned the other day, I'll try to put some assignment up that's completely not mandatory, completely optional for you if you want to do something over the break. If you're like, I got to keep up my C++ skills, that's cool. All right. The other idea is to like totally chill, forget everything you knew about C++, and like relearn it next time. All right. So I don't know. I don't think you'll completely forget it in a week. All right. Today we're going to talk about a couple things. First things first, I'm going to briefly mention this thing called the public_HTML public_HTML folder that you guys used in the lab yesterday, all right, and Monday. And then we're going to talk a little bit about websites in general. And then I'm going to talk about this thing called a heap, which, if you remember from last week, or rather from Monday, all of Monday's lesson was like total setup for this data structure. OK, so we will see why these are cool. And this is kind of one of my favorite like data structures. So it's another one of those. I'm a nerd, I know, but it's kind of exciting the way it all works out. So you'll see. You'll get plenty of time today to like try to figure some of these things out with heaps as well. OK, first things first. So the public_HTML folder. Did you guys like the lab the other day? A little different. You got to do got to put stuff on your web browser and all that. What you guys did was the back end to the try. In other words, the back end of the web page. And you did it in C++, which is a little bit weird. Most of the time, back end languages are everything from PHP or Python, or these days, a lot of people like this thing called Node.js, which is JavaScript. And most of the time, back ends are written in those languages, which are scripting languages. And you don't have to make them and whatever. It just kind of runs them straight away. And what we did was I had to kind of be a little sneaky about how to get your C++ to run, basically because the system administrators don't trust you to run code that's not what's called Perl, which is odd because that's a weird choice. But for whatever reason, they don't let you do that. You can run that, though, so we had to sneak it around. But you guys wrote the back end. And you could write you could have looked at the front end. You could have looked at the actual HTML and JavaScript code that's running the actual web page too. But the point is that you actually have this thing now called the public HTML folder. It's available all over the world. If you want to show your parents what you did in lab yesterday, you can like say, Mom and Dad, go to this website. It's totally available. And you can do other websites too. If you really want to put stuff there that people can go to, you normally do it in what's called an index.html file. And an index.html file is like, hey, here's my first page. You've probably seen it a million times on the internet. OK? You go to get there, as it was done in the lab, you go to www.cs.tufts.edu/tilde, your username. And then if you have an index.html, that's all you need to do. OK? So it's kind of neat in that sense. All right? So you can set it all up. You can build your own web pages. Normally what we do when we create an index.html file, we actually change the permissions on that file. You know how you guys can't read my files, right? You can't go and like see what the midterm looks like beforehand. You can try, but hopefully I've got it set up that you can't. You can actually change the permissions on a file. You use a command called chmod, C-H-M-O-D. And that says change the mode or the permissions on a file. If you want to change index.html to be readable, you would do chmod a plus r, meaning all users get to read it, right? And then you do index.html. If you want to have a folder, you'll have to actually change the permissions to be rx for also executable, which means not only can you read it, but you can read things inside that folder. So it wouldn't be for index.html. It might be for something like, for instance, lab 6, which is what you did. Now, I don't know if you noticed, but the make file actually ran this on your files when you typed make, so that it turned them into both executable files and readable for the web page. Yeah.
So hypothetically, if you move the folder away from public HTML, it wouldn't work with the graphics?
Yeah, well, it wouldn't. Right. If you moved it away from the HTML folder, when the web server looks for your file name, it looks to see if you have a public underscore HTML. If you don't, it won't run anything, won't do anything. So your stuff has to be in this folder. And that's where it goes to when it looks for your username. So that's that. So you can do all these things, and it's kind of fun. Again, you might not be doing it for a little while, or you could learn it on your own. But we have a class here at Tufts called Comp 20. I'm not sure why I really plugged Comp 20, because everybody already wants to take it. But if you like this stuff, sign up for Comp 20, and you'll learn how to actually make your stuff interactive for the entire world to see, which is kind of fun. OK? Any questions on your public underscore HTML folder? Yes?
Will we have access to that, like, say, over the summer if we want to
It'll be there this summer. It'll be there at the very least until you graduate, probably even a year or two after. But you wouldn't want to bet on after, but you can ask for the policy. They have policies and whatever. You probably have one by virtue of your Tufts username too. I'm just not sure. Yeah, but it is kind of fun, and you get to do lots of like interactive stuff. So I hope you enjoyed that lab. OK, so on Monday, where did we leave off? We talked about these things called priority queues, right? And a priority queue, remember, we had priority queues. We built basically 2 priority queues, and then we kind of quickly sketched out a 3rd priority queue. We had a dynamic array, we had an unordered list priority queue. Unordered. We had an ordered list for a priority queue, which was both of those were using arrays to be your unordered and ordered priority queues. And we also used a binary search tree ordered queue. OK? And we had some trade-offs, right? We said what? We said we could do insert, right? And remember, insert took a key and an element into your priority queue. And what was the unordered asymptotic complexity to insert something? You remember? Constant, right? Order 1. That was beautiful, right? We also had a remove min, right? And what was the 3rd one that we had? It was actually min element, right? Min element, which returned the element. OK, for an unordered list, to do remove min, actually, let's look at min element first. To do min element, what was the asymptotic complexity for an unordered list? It's not constant in this case, because you have to find it first, right? It's unordered. So it's linear, which wasn't so good. And then there was remove min, which you first have to do what? Find it, which means it's going to be at least that. And then is there anything else to do once you find it? A swap, which is not a big deal, right? So this is also linear behavior. For the ordered list, right? For the ordered list, we had slightly different qualities here, asymptotic qualities. For the ordered list, right? When you're inserting into an ordered list, how long does it take to do that insert? It's linear, right? But then once it's ordered, right, you get the remove and the min element are both what? Constant, right? Which is exactly what we love, but there's trade-offs here. OK, the binary search tree. We didn't really go into too many details about this. Best case for binary search tree was, well, not really best case, but the average case for a binary search tree is things that we normally like. What is the average case? Logarithmic, right? Especially, log n, especially if we have a binary search tree that's actually balanced, like an AVL or a red-black tree or something. Okay? But the worst case could be as bad as what? What is it? Linear, right? Because you could insert into your binary search tree and make it into some like a linked list sort of thing. OK, so that's so good. Not so good. And by the way, these are going to be the same here all the way across, right? Because for a binary search tree, pretty much all the operations are logarithmic, or in the worst case, linear. OK, so not the best behavior in the world, all right, but not so bad. Binary search tree is not too bad, although binary search trees aren't the easiest things in the world to actually code, as you found out, right? Especially the balanced ones. But that's that. OK, so that's where we left off the other day. Turns out there's another way to build a priority queue data structure that's perfect for what we're trying to do. Okay? It's this thing called a heap. Let me erase all these guys. It is this thing called a heap. And a heap has basically two things about it that are important. Okay? It's got an invariant. It's kind of got two invariants. Really, we want to think about it as one invariant. But a heap has the following we'll call them both properties. Okay? Heap property number one is that all nodes have higher priority than their children. Okay? Higher priority than their children. Which is interesting because that's different than a binary search tree. It is, by the way, it is a tree structure. So it's a tree structure. Okay, it's a tree structure such that all nodes have higher priority than their children. The key is a higher priority anyway. Okay, let me draw a couple out here. Let's say we have 5 and 8 and 10 and 20 and I don't know, 9, and let's leave that one at I don't know, 15. Is that a heap? If we're saying that high priority is the lowest number. In particular, this is called a min heap. A min heap. Okay, it's called a min heap because the minimum is the top one in there. Okay, this is a min heap because, again, all children are a higher priority. There is no ordering between the two. Okay, the sides don't actually matter. You look at your top one here, the root, and it's got to be all of its children underneath have to be a lower priority, which is exactly what this is. Okay, so this is a heap. 5, 10, and 12. That's a heap. How about 5, 12, and 10? Is that a heap? Ah, okay, so those are both heaps, and that's what we have to contend with for a heap. And it's a binary tree, but it's different in that you don't have to worry about like the ordering of children at all. You just think, if I'm a node, all my children are going to have a lower priority. Okay? Now, one other thing. I was very explicit about the way I drew this one. Any ideas? Can you give me a feel? Let me draw two more things on this one. Let me draw this one at, I don't know, 18. And then let me draw one over here, 21. What's interesting about this tree? We talked about it way back when. Yeah. Anna.
You maybe have to start on the left and the right.
Yeah, what do we call this kind of tree? This is like one of those vocabulary ones. Complete tree, okay? The next thing I insert has to go right here, and it has to be bigger than 20 because we said that it in the sense of keeping it as a heap. Okay, so this could be 25 or something. Okay, it's a complete tree. So that's kind of property number 2, complete tree. Okay, in that this is now it has to be, and for those of you who didn't quite remember what a complete tree is, all the levels are filled except possibly the last one, which is filled from left to right. Okay, so everyone down to the last row has to be filled, and then the last row can be partially filled, but it has to be left to right. We could not have something underneath the 15 or the 18, and we couldn't have anything. We couldn't have the 25 here and not the 21. Yeah, Nate?
What happens if you add something very large and then add it afterwards that aren't that large?
Yeah, this is a good question. So how do we actually deal with this in a heap? Guess what? We have a way to do that. In fact, I'm going to make you guys think about how to do that in a few minutes. Okay, but let's think about a couple other things before we do this. Okay, we know that they're completely filled. A lot of times what we will do is we will actually draw these guys in as like empty boxes. Okay, so sorry about getting a little small here on the bottom of the board, but we will draw in the other nodes as like empty boxes to show that they're still there as nodes, but they're like not filled. Okay? These ones are called like inner nodes that are filled. Outer nodes are one that's like that aren't filled. Okay? Inner versus outer. And that's the way, normally the way we would build it. Okay? All right. So here's my question to you. What is the best way to actually store a heap in memory? Okay? Here's what I want you to do. You've got the, I'm going to leave the question pretty much at that. What's the best way to store a heap in memory? Okay, you've got lots of options, and some of them are pretty like straightforward, but you come up with the best way to store this. So talk to your neighbor for like 3 or 4 minutes and come up with the best way to actually store a heap. Okay, go ahead and try it. Talk to your neighbors about this. That's it. That's all I get.
Oh yeah, it's that wire.
Oh, it's that wire up there.
I think that can go down, that one back there.
This one can go up though, can it?
Yeah.
No.
I think you guys did.
You know, you'd think the physics department would have a better way of doing this. Ah well. Forget it. I'll do it over here. Any ideas? No? Okay, so I've actually been keeping my ear out. I've heard a couple of interesting answers here. What's one like way that coming from like last week you would have gone, here's how we're going to store this? As a, not as a stack, no. As a what? As a tree, right? Where you'd have nodes. You'd have 5 has a left and a right, and 8 has a left and a right, and they all have lefts and rights. And that's a perfectly legitimate way of doing it, right? You could store a heap as a tree structure. But there's actually a slightly better way to do it. In fact, a much better way, and according to some people. Now, I heard these guys talking about it. Anybody else have? I'll give you a chance once. Let's let one other person, if they start to do it, I think I know it. I think you've got the right idea. Janelle, what do you think? Dynamic array. That's what you were going to say as well. OK, anybody else have any other ways of doing it? Yeah.
I don't know, this might be overcomplicated, but I was thinking that you could have arrays with a struct inside each of the like spaces with 2 pointers, and every level would have like 2 to the end, like
So you have so it's an array or a node?
well, each level would be a different array.
OK, so there's an array here. Oh, let's do it this way. So maybe an array like this, and then one that's like that.
2, and then
The next would have 4. OK, that's like you're going to have to keep a lot of pointers that way, right?
easier access.
It's easier what?
Like each level you can access.
Oh, yeah, for each level, you can immediately access that. That's very good. Yeah, that's very good. Comment. Yep. Oh, OK. What's your suggestion?
I would do an array, and then you could do the indices like nodes left out and the next time.
Oh, OK. So you're going to just do one straight array. OK, that's what I think a couple other people were saying as well. Somebody else have their hand up? Nathan, what do you think?
Yeah, I think, well, if for the series of arrays, you only need 1 pointer per array. You can just access any element using that 1 pointer and then hop onto the array.
Oh, I see. So you're going to have 1 pointer into the array. Yeah, it's kind of what a dynamic array does in general, right? What's nice about an array is you can index any one immediately. OK, yeah. What were you guys going to say about the pointer, about the array? And Janelle, maybe what you were going to say too.
I was going to say that you have the dynamic array, and each level is represented by a power of 2, like an index and power of 2 kind of. be within 2 to the power 0, greater than 2 to the power 0, but between 2 to the power 1. So it'll be at 1 and 2.
Okay. So for this one here,
Yeah.
which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, or I should just say 1, 2, 3, 4, 5, 6, 7, 8, 9. How many things in our array are we going to have?
We're gonna have filled 9.
Okay.
We're gonna have space for those.
Space for this extra row too. Is that what you're kind of thinking too? Okay, yeah, I like that. So in this case, it's going to be 16 total spaces, right? Which in terms of 2 to the what is what? 2 to the what? 2 to the 4. But where does that 4 come from? Any idea?
The level of
The height, right? What did we say the height of a null tree was from your homework assignment? 0, right? Or -1, right? -1. So the height of just the root would be 0. Height of these two would be, this one would be 1, 2, 3. So if this is the height of 3, it's going to be 2 to the height plus 1, right? Which is for well, there's only 15 things here. So technically, you could probably keep a -1. You only need 15 spots. Let's keep 16 because computers are really good at calculating powers of 2. Believe it or not, it's like super duper fast. We might as well do that. Another reason we kind of double things a lot too. But anyway, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think I got that right on there. OK, so that's it. So then what are we going to do with our numbers in this tree then? How are we going to store them in there? Yeah, what do you think?
In Latin, they go back order traversal.
OK, so you're telling me that what's going to go first? The 5, and then 8, and then 10, and then what? 29. Oh boy, I wrote too small. Sorry. 15, and then 18, and then 21, and then 25, and then there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Perfect. OK, so that's actually exactly how we would do it. Now, what's interesting about this, so believe it or not, this is actually a good way to store the tree. And by the way, what's nice about this is that you can definitely tell how many they're going to, how many you need, because what's the case? Because it's what? A complete tree. And if it's a complete tree, you know it's going to have this nice orderly structure, right? Could we, I'll do it over on this board. For the video, actually. Could we do a regular old binary search tree? 10, 20, 15, I don't know, 14, and 17, and maybe 5. Could we put that in an array like this? Sure, you could. You absolutely could. What's the problem with it? The what? What about the spacing? Well, there is. You could do this, right? You could do it, and you could just say, fine, OK, I'm missing this one, and I'm missing, this one would be 1, 2, and this one would be 1, 2, and I'm missing that one, and that one, and that one, and that one. And then, let's see, there's some others down here that I'm missing as well. And then that's, and the right of 20 I'm missing, and then that way and that way. And you could come up with the complete part of it. But yeah, you could do this and perfectly well put it into an array, but you're going to end up with an array that has what? Lots of empty spaces, right? You would do that and it would have lots of empty spaces. What's nice about a heap is that all these empty spaces are for a purpose because that's the last level you're going to be on, and they all happen to be at the end. Okay? Now, I'm going to be slightly sneaky here. Yeah, question. Let's find out. We'll find out how we're going to do the actual insert and remove. Let's find out how we do that. First things first, I'm going to be really mean, although it's easy on the board. I'm going to shift everybody over by 1. OK? And I'm going to do that for a specific purpose, and you'll see why. This is going to be index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, like that. OK? And I'm going to shift everybody over. And we're going to say that this 0 one, this is like blasphemy in some cases, right? Because computer scientists, we all We all count by 0, and now I'm saying, no, 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 the first one's going to go in 1. There's a good reason for that, and I'll show you that in a second, right? But what's nice about this, okay, once we have it in this form, watch this. Which index up here is 20? 20 is in index 4. And again, I'm sorry for not writing big enough. 20 is in index 4. Which index is its parent in? 2. What's the relationship between a child and its parent? Divide by 2 in this case. What about 9? 9 is in position 5. What's its parent, its child in? Right? It's divided by 2, but we have a special way of writing that, actually. We say that to find a parent, right, we actually do a little arithmetic, and it's going to be whatever index it is, divided by 2, and then these little guys, which is called, anybody know what that's called? It's called the floor function, which basically means go back to the nearest, or to the next smallest integer value. Okay? So to find the parent of a heap index, you start at whatever index it's at. So let's go to, let's try 21, which is in index 8. Index 8, its parent would be 8 divided by 2, which would be 4. We better find 20 at position 4, which we did, right? Okay? Because it was 25 divided by 2. Yeah? Okay, or did I say 21? 8 divided by 2 gives you 4. That's it, right? And for 25, which is in position 9, 9 divided by 2 is really 4.5. But the floor function says, nope, it's 4. OK? So far, so good? All right, so that's how you find the parent. Anybody want to tell me how to find your child's position? How about your left child? Multiply by 2, right? Left child, 2i. Right child, 2i plus 1. All we have to do is a little bit of arithmetic, and we instantly find your child or your parent. Your left or your right child or your parent. You see why I get excited about this? This is kind of cool, right? It's just arithmetic, right? It's an array. And somebody in the earlier class said, wait a minute, so you're telling me all of this tree stuff is only for our benefit? And I'm like, yeah, it's always only for our benefit. I mean, I guess a node structure would be more, but really, the computer likes it like this. We like to look at it like that because it makes more sense. But if you were in the matrix, you'd like this better, right? Because you'd be like, well, it's right there, and I can do arithmetic, and I can find parents and children with just doing a little arithmetic. Trust me, a computer dividing by 2 is the fastest thing a computer can do. There's almost nothing faster. Yeah?
So if we're going to use this kind of structure to store data, what are we going to put in the 0 spot?
You're not going to put anything in the 0 spot for now, right? You're just going to kind of leave it out there to mock us, right? Until you want to do maybe some manipulations. Instead of having another variable that you create, use the 0 spot as a temporary spot, right? Why not? Okay. One other thing we have to talk about here, there's just the size of this. Okay. The size is how many actually exist in here. Okay. We call it the heap size. In this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So the heap size is 9. The next place we are allowed to insert into a heap is where? 10, which is here because it's the left child of 9. And remember, we couldn't put 1 at the left child of or the right child of 18 or any of these other ones. You have to fill in from left to right. So it's actually the next location is heap size plus 1. Okay? All right. So that's how we're gonna think about this. The arithmetic makes all of this really cool. Okay? Really cool. All right, enough of the details of that. Let's go back and talk about why this structure is so good for a priority queue. Okay? For a priority queue, we said there were those 3 functions we talked about, right? We said the first one we'll use, why not min element. Min element. Okay? We also have insert item, or just insert. Insert, right? Remember, we have to insert the key and the element. Okay? And then we have remove min. Okay. If you have a heap Where's the minimum element? Always at 1, isn't it? Because no matter what, if something else was smaller here, it would have to be in position 1. You'd have to change things around so it's in position 1, because the root is always like the highest priority, because all of its children are the highest priority. So in order to do min element, right, it's the easiest function in the world. Return our heap at location 1. What's the asymptotic complexity of that? Constant, not linear, constant, right? This is constant because you're just returning one thing. That's it. Beautiful. So we've immediately got a great benefit out of this. The min element is always right at the top of the heap, element 1. OK? All right. So that one's not too bad. Let's look at insert for this function, or insert item. Right? If we want to insert an item into this heap over here, how are we going to do it? This is what you need to think about for the next few minutes. OK? What I'm going to do is, while you're thinking about that, I'm going to draw a bigger heap up here so I can like not have it all scrunched up at the bottom. But think about this for a minute while I'm redrawing it. Think about how we might insert into this and keep the heap property. OK? Think about that. Talk to your neighbor about that, and take a few minutes on it. OK? Yes. Yep. The children have to be lower priority. That's it. Right? Either side. A sorted priority queue? You tell me. Maybe, maybe not. Too small. Whoops. Did something wrong here. That should be 8. That should be 8.
The order on each particular level doesn't matter.
The order on each particular level doesn't matter. Yep. Yeah. Yeah, sorry, I changed it to 8. It would be similar to the idea of the binary search tree where you had to do like duplicates or something, but we're not going to worry about duplicates right now. Okay. Yeah. Yeah. What if you're introduced to like 2? I don't know. Let's find out. You figure it out. I'm not sure just shifting it would actually work, believe it or not. Not sure. Yeah, you're messing up the parent-child relationship, definitely. Yeah. All right. Does anybody have an idea of how we might do an insert of 9 into this, or insert of anything, really, into this? Now, somebody earlier in the other class cheated. They actually, well, I thought they looked at their notes. It turns out they're taking Comp 160 at the same time. This is actually a prerequisite for Comp 160, and this person is taking Comp 160 at the same time, and gave me this like beautiful answer for the next one, actually. And I'm like, wow, that's really, did you look at the notes? No, we did it in Comp 160. I'm like, oh, that's not cool. You're like, try to let people think. So who has an idea, who hasn't looked things up before, or whatever? What do you think?
Would you just insert the 9 after the 5, move the 10 as a...
Which side of 5?
To the right of 5. Well, my left of 5.
So here.
Yeah.
OK, so you put 9 there, and then what?
You make the 10 a child of 9, and then you take everything from the bottom level, and you start making them children, like start filling up the previous.
So you basically make this 9, and then 10 becomes here, and then what happens to 11?
11 is still attached to 10, so it gets shifted.
Oh, 11 is shifted down this way, and then these ones?
For 9's other children's, in order to preserve completeness, you just attach 23 to the other child of 9.
Okay. Okay. So I think that might work, but it's going to be really intense, like having to go jump down and whatever. Remember, part of these things are like trying to. Part of the idea here is trying to like do something very orderly that you don't have to jump around. But yeah, that's very good. Yeah. What do you think? Good idea.
The first empty index in the array, and if
Ooh.
that it's like halfway its parent.
Okay, so where would I put? What would I do in this tree for 9 right now? What would I do?
So you know you're going to go to the left of 11.
Okay, this is a very important point. The next thing that has to end up here has to be to the left of 11. So we're going to have to add a node there, no matter what this thing looks like in the meantime. That's the way it's going to have to end up, right? So I like that start. OK, and then what are you going to put there?
You put 11 there.
Put 11 there. So put its parent there or something?
Yeah.
OK. OK.
And 11 gets 10.
And then this one gets 10. OK.
And then but every time you put something in, you check to see if the parent is less than what you're inserting.
Every time you check to see if the parent is less than you're inserting. OK, yeah, I can buy that sort of idea. I think it's actually going to be a little bit simpler to think about in a slightly different way, though. So I like what you're doing, though. Anybody else have an idea? Alex, what do you think?
Sort of going to be thinking out loud as I'm doing this.
Go right ahead.
You go through each level and you find if there's one that has a higher priority that has an empty child, you put it in there.
OK, hold on. If you find one that has an empty child that has a higher priority, what if I was inserting something like, let's say I was inserting, what's a good example? Well, 9 is a good example here, right? If we do this here, then it would go here somewhere, right?
Well, I'm getting there. If there's one with higher priority, so I would go to 8. Yes, 8 has higher priority, so you go down. But if you find one, if there isn't one, you find the lowest priority one that's available. You put 9 where that is, and you insert that one.
OK, again, I think that might work. But again, it's going to be like lots and lots of code.
Yeah.
OK, so I think we're getting there. Janelle, what do you think?
You would compare, before you even put anything in that spot, you would compare 9 to 11.
Oh, OK. So why don't we just put something in that spot? What's the thing we're inserting? 9. Let's just put it there. Just like go wild and put it there, right? We're going to put it there. And then what do you have to do? Because this is not a heap right now. What do you have to do? You compare it to its parent. And can we find its parent easily?
Yeah.
Sure, it's arithmetic. Compare it to 9. And then this one goes, so 9 and 11 swap because they have to. Then what do? You repeat the process. Oh, it's recursive. This is beautiful, right? And then you repeat the process here. And then 10 and 9 swap. OK? And then you repeat the process, because we're not done yet. And then you check against there. And if you ever get to a point where you don't have to swap, guess what? You're done. Okay, let's do that in the array itself. I would add 9 here. Okay, I would add 9 there, and then I would say compare 9 to its parent. So the parent of 9 is so it's at index 10, divide by 2, we go to 5. So it's 9 versus 11. Okay, because 9 is less than 11 or a higher priority, we swap them. Okay, 11 and 9, and then we have to check this one's parent. 5 divided by 2 is 2, right? 2.5, but 2. So 9 versus 10. Okay, because it's at index 2. 9 is less than 10 or a higher priority, so they swap 9 and 10, if I'm getting my math right, 9 and 10. And then what's the parent of 2? 1. 5 and 9, they don't swap. Okay, so do you see how that works now? What's interesting about that is you just go with where it has to go, and we call this process, this is another fun thing about this topic, we call this process bubbling up. Because this one goes bloop, 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 right? As far it bubbles up as much as they call it. It's also called up heap, if you want to call it that, right? Okay, but I like bubble up. I think it sounds more fun. Yes? Let's see if 11 would go as a child of 9. Remember what a heap says. A heap is parents are greater than all of their children. Greater priority, higher priority rather. So 9 is a higher priority of both 12 and 10 and of 11 and 43 and 22, and that's all we care about. Right? 10 is a higher priority than 11. Check. 12 is still a higher priority than 22 and 43. Okay? Now, somebody asked earlier, what if we added 1 to this, right? Where's it going to go? To the right of 10, because it's got to. That's the next place it's got to go. Bubble up. How does bubble up happen? Compare 1 and 10. Swap, because they have to. Repeat. Recursive. Woohoo. Right? Compare 1 to 9. 9 and 1 swap. And then compare 1 to 5. They do swap, right? Right? This is the guy with the knife sticking out his neck that goes to the hospital, right? Right? That's how he gets into the queue. You put him down here, and he goes bloop, 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 bubbles up to the top, and they wheel him in and start surgery. While you're sitting there with your broken leg, you know, sitting around waiting for all the other priorities to get handled first. Right? OK, everybody get that? 1 would swap with its parent, which is 5. So 1 and 10. And then 1 swaps with its parent, which is 2. 1 and 9. And then 1 swaps with its parent, which is 1. So 1 and 5. What's the asymptotic complexity of that? It is log n, okay, in the sense that each operation is maximally log n. In other words, you have to, at the most, bubble all the way up. And because the height is logarithmic, then it's the log of the log n, right? Turns out that it's actually provably constant, actually. Okay? It's actually provably constant on average. Okay? Not worst case. Worst case is certainly logarithmic, and that's what we can see from this. But most of the time, you don't have to bubble all the way up. When's the only time you have to bubble all the way up? When the knife is sticking out of your neck, right? That's when you have to do that, right? You only bubble up when you're the absolute highest priority, right? And then you have to bubble all the way up. Every other case never has to bubble all the way up, okay? In the notes online, there's a little link you can watch to read to a paper, or a link that goes to a paper that you can read. It's kind of intense. I tried reading it, and it's pretty intense. But it proves, and it was in a conference, so I gather somebody looked at it and went, yeah, that's actually a good proof. And they and proved that it's average complexity of 1, which is cool. Okay, complexity of constant behavior. Okay, everybody gets how to insert now. Okay, are you ready? You ready for remove min? Go. Figure out remove min. Take a few minutes to try that out. Okay. Hey. You have a question? No? You figured it out? Woohoo! You have an idea too? What's your idea?
You set the root to like a temp
Okay.
thing, and then bubble up whatever you're moving to the top, and just remove it from the top, and then set the temp back to that.
Bubble up what you're removing. We're removing 1. It's the minimum.
Oh, you only
Yeah. I know you're right on the right idea though. You're on the right track rather. Yeah. Figured it out. Did you cheat and look? No. Yoo-hoo. What's up? What do you think?
Wouldn't you just compare the children to the parent and then you bubble all the way down?
Well, the parent is 1 right now, right?
Yeah.
And we're removing that. And then what happens then?
So, well then, so you have to legitimately remove the entire root first?
No.
I
mean, not really. Remember, there's no nodes here, right? There's just an array.
Oh, yeah, that's right. You could just like take out 1 and then move all the other ones.
So you're gonna shift them all?
But I figure, like, why do that when you could compare it to its children and then bubble down? So 5 and 1 would switch places, then 1 and 9 would switch places, then 1 and 10 would switch places.
So you're gonna bubble down the one, even though it's higher priority.
Well, you bubble down it and then remove it because it is the highest priority.
What if it goes that way?
What if it goes one
What if it bubbles down the wrong way? What if 5 and 8 were swapped and it starts bubbling that way?
You compare the children. I don't know.
Oh, you're getting there. You're definitely getting there. I think you're on the right track. Definitely on the right track.
But have you ever do you know what a hash table is?
So you take off the 1, and then you basically find the min in each level, and bubble that into the empty space.
Find the min in each level. Okay, that might work. The problem is, so let's say 5 and 8 were swapped. So then which one would go here? 5 would go there, and then what happens here?
Go to the next level, find the highest priority in that level, and push that up to that.
But what if something down here was still a higher priority than these one, or something else? Like maybe what if all these were the lowest priority? I mean, these two are not these two don't have to have an ordering between them, right? This could be 5 and this could be 8, and so any of these could have a different ordering too. They don't necessarily. These ones are not necessarily smaller than these ones, right? So you got a little bit of an issue there, but I like the way you're thinking about it. Okay, does anybody think they have an idea? I've heard lots of great ideas actually. Lots of great ideas. Let's see if you just answered. You've answered one, Katie. What? Yeah, Hannah.
Well, we were working together.
Okay, you're working together. Go right ahead.
Okay, so we talked about how the minimum is at the root.
The minimum is at the root, yes.
Yeah, and that you would just like return, you put that one in like a temp, like return.
Yeah, that's going to be gone. You could return it or not, but whatever. It's going to be gone in the end. Okay.
And then we compare which child is smaller, and then like move that one up, and then call remove again recursively.
Okay. So I tell you what. I like that idea, but what if I did this? What if I made it 8 and 5? Everybody's still okay, I believe. Okay, yeah. What if I made it 8 and 5? So you're saying that the 5 would now go here?
Yep.
Okay, and then what happens here?
Oh, I see what you're saying. Yeah, 13 would move up.
13, and then what happens here?
We're talking about deleting that one, but then it wouldn't be a.
Wouldn't be complete anymore. Yeah, I like what you're thinking. But you've got an issue with like now it's not complete, and you can't just move like one over. It's just not going to quite work, right? So let's rethink that a little. Let's go back to the original for a second. Okay, I like the fact that the 1 is going away. Anybody else? Yeah, Katie. Oh, because you've done it before? Oh, how are you in 160 as well? Okay, give everybody a hint.
You have to swap 2 things.
That's a good hint. You have to swap you can swap 2 things, but remember 1's going to be gone. How about this? You have to put something else where 1 is. That's probably about the same thing, right? What do you think? 22 over there. Guess again. Andrea? Okay. Why 10? Okay. At the end of the day, doesn't that one have to be gone? Remember how when we put that in before, we said, look guys, it's got to be this one. So at the remove, doesn't it have to be missing? That one has to be missing, and that's the one that has to be missing, right? And it was a 10. So where did you want to put that 10? Put the 10 here, and now the whole heap is screwed up. But Hannah's saying it right now. What are you going to do? Bubble down. We've got bubble up, and of course we have bubble down as well. How do you bubble down? Yeah, go ahead, Alice.
Once you're moving, you just insert on the value that you
Remember, insert is doing bubbling up. So we've got to bubble down now. So I think you got to think about what happens to that 10. Well, first of all, which one's really going to be the root next? Who's the guy that doesn't have the knife sticking out his neck but has like a really bad paper cut? Right? It's 5, right? Because 5 has to be the next one, and it has to be the next one. And it turns out that for a certain level, that's the only one that can go up there is the one that's the minimum of that. Well, the minimum of the whole level there. It has to get up to eventually up to the top, right? So in other words, priority 1 has to be here, right? Priority 2 has to be one of these two. It could be, this whole thing could be priority 3, 4, 5, 6, 7, 8, and this side could be like all the rest. But one of those two has to be the next one, right? Because everything below them have to be minimum, and kind of if you do the proof, it shows that that works. But which one's going to, so you're going to do a comparison here between which 3 values? 10, 5, and 8. And you're going to swap the 10 with which one? The one with the smallest or the highest priority, right? The bad paper cut, right? So 5 and 10 goes like that. OK. And then not quite done yet, are you? What do you have to do now? You have to bubble this one down, too. So we have to check again 10 versus 12 and 9. So what happens? It swaps with the lowest one, right? 10 and 9 swap, right? And then one more comparison. You have to compare until you stop having until you don't have a swap anymore. 10 and 11, do they swap? No, they're fine. Is this a heap again? Woohoo! Is 5 the next highest priority after 1? It is. OK. Got a question?
No.
OK. All right. So you get the idea here. Let's try another one. Let's remove 5. Here, by the way, I'll write this down for a second. 1, and then we're about to remove 5. OK. So remove 5. What do we do? 5 goes away, right? 5 is the one that's getting removed. So then we put the 11 up there, because it's going to look like this eventually. And then 11 bubbles down which way? To the right, because the 8 is now the next highest priority, right? Stubbed toe or something. Right, 11, and then what happens? You do a comparison again, and you're done. And that's it. OK. And then 8 is indeed the next highest priority. Our heap is indeed still a complete tree. Right? And we're good to go. OK, so wait, what? No? Did I swap? Did I miss something? No, 10 and 11 are fine. Why are 10 and 11 fine? Yeah. 10 is not a child of 11. Right? 10 and 11 are perfectly fine because all it matters is 10 is a child of both 9 and 8. Right? And it has to be a lower priority than 9 and 8. It could care less about 11. Right? What'll happen? Let's do another one. You ready? Let's do another. Let's do 2 more removes just to prove a point here. Well, the next thing that's going to get removed is hopefully 8. Right? And the next thing's 9, and the next thing's 10. Let's quickly remove 8. 8's going to come out. We're going to take 8 out. We're going to put which one there? 43. That one's going to get bubbled down a lot. 43, which one does it replace? Or which one does it swap with? 9. Right? 9 and 43 are not done yet. 10. 10 and 43. Are we complete tree? Are we a heap? Yeah, we're good. And we've got what's coming out next? 9 is, right? 9 is coming out next. And then 9 gets replaced with 22, because it's the last one here. 22 has to bubble down. What's it swap with? 10. Doesn't swap with the 11, right? 10 got all the way up here before 11 did, simply because of the fact that it was correct bubbling down, right? And we're not quite done yet. 12 and 22 need to swap, right? 22 and 12 need to swap. So now we're good to go in terms of another heap. And even though 10 was hanging out way down here and like a lower level than 11, it was fine. In the end, it got up as a higher priority. OK? That was fine. And then 10 would come out, et cetera. Hey, what am I creating over here, by the way? A sorted list. This is one way to sort things. Everything goes in a heap. And then we just do remove min, remove min, remove min until we get a nice sorted list. This is called a heap sort, actually. A heap sort. OK, you'll practice a heap sort on the next lab. In fact, you'll practice remove min on the next lab, like a week from now, because we got spring break. But you'll practice the remove min. Remove min's a little tricky. It's tricky because the left and the right, you have to see if both are like there, first of all. By the way, if you have a right child, what does that mean about left? Has to be a left child. It's one thing to do. But if you have to compare against both and then swap with the one that makes, there's a little bit of a couple like special cases in there. Not really special cases, but different cases in there. OK? All right. So that's remove min. OK? And that's pretty special. We did not talk about the logarithmic behavior, though. What's the logarithmic behavior of a remove min? And I'll give you a hint. The 43 gave you a very good example of that. Well, actually not quite as good, but what is it now?
Because you wanted to get all the way down, it has to be log n.
Yeah, well, it really does have to be more or less log n, because the odds are, if you're taking something on the last level, it's going to be pretty low priority to begin with. So it's going to have to bubble pretty far down on average. So this is definitely log n behavior. OK? Log n behavior. OK, so that's how we do removes and inserts and min element. OK, we've got 2 logarithms and a constant, which is better than any of the other ones we checked before, and pretty darn easy to implement. It's in a stinking array, which is so easy to implement, right? So that's great. OK. Now, I have one other question for you. OK. What's the best method for building a heap from scratch? Let me set it up for you. Let's say we have the following numbers: 14, 9, 13, 43, 10, 8, 11, 22, and 12. Those are not in any particular order. In fact, they should be random. OK? What's the best way for creating a heap from these numbers? Think about that for 5 minutes. OK? Think about that for 5 minutes. And what I will do is start erasing. I can set this up.
Are you putting all those numbers into the computer at once, or are you just like, okay?
You're putting them all in at once, and you can do whatever you want with them. Right? I hope we're all thinking and not stuck. Or maybe stuck in thinking, but done. Are you done? Like you can figure it out? OK, I see. OK, I see how it is. All right. OK, somebody give me an answer. What do they think? Somebody hasn't gotten a chance to speak yet, if you want. I know you've already spoken. I'll give you a chance in a sec. You said something, no? Anybody else? You want to think for a few more minutes? Or are you done thinking for the day? It's the Wednesday before spring break. I see how it is. All right. Nasifa, what do you think? So you could put the first 3 in, parent and children, and bubble up. isn't that just basically saying insert each one in order? Like just insert, do the bubbling up, insert, do the bubbling up, insert, do the bubbling up, right? So you could do that. Okay? What did we say for insert, this was logarithmic, right? And then you have how many that you have to enter? N of them, right? So that's going to be n log n behavior is what it's going to be. Okay? And that's pretty good. Like that's not too bad. Okay? That's not too bad. But the thing is we can actually do better. Yeah, what do you think?
Well, insertion sort would be n squared, right?
An insertion sort would be n squared. So this is better than insertion sort. So definitely, yeah, I like that. So this is definitely better. That's not a terrible idea to just insert, right? Turns out we can actually do a little bit better. This is tricky. I don't know that I would have necessarily figured it out on my own. What do you think now? A stack. Yeah, you could do some. You're still going to have to do a lot of comparisons, but that's a good point. How about this? Let's be like wild again. Did you have a question, Janine? Joe? Ah! That is a wild idea. Yeah, so I tell you what, I can barely see that. Read these off to me. 14. Oh, thank you. I could have just swapped it. You're right. Thank you. 14 and then 9. 13. Sorry, too fast. 43. 10. 8. 11. 22. 12. And that's it. OK, so there's our array. The heap size is 1, 2, 3, 4. Heap size is 8, right? 9. 1 to 9, of course. OK, heap size is 9. By the way, once it's in the array, it's really easy to put into the actual heap so you can draw it pretty quickly, right? 14, 9, 13, 43, and then 10, and then 8, and then 11, and then 22 and 12, right? 22 and 12. Now, this is by no means a heap, and it's like blasphemy to put it in like this, right? This is just a binary tree. That's it, right? Complete binary tree for what it's worth. But what were you going to say now? Starting with the last element.
Compare and
Bubble up.
yeah.
Problem with
I
the
don't know what goes after that.
yeah, I mean, if you do that, then the 9 would end. Well, this 12 would stop here.
Yeah.
OK, and then what would you do? This one and bubble it up, or something else?
If that first subtree to be,
Yeah.
but then work up, but I'm not sure.
OK. I like what you're thinking. What do you think? What do you think?
Why don't you take the smallest element from each level and bubble that up?
Smallest element from each level and bubble it up.
And then you look at the 13, the 14 is 9. That would be a good level. And then you go down to the second level and it would be like, oh, 8 is the smallest level there.
Yeah, again, this is good. This is a lot of comparing, though. And remember, going level to level isn't the easiest thing in the world, right? We want to do a parent-child sort of thing a little bit easier if we can do it. But how about this? How about we take 12 and we bubble it down? Is it going anywhere? I know you're going to say that's weird, bubbling it down. No. Then we do 22 and we bubble it down. Is that going anywhere? No. How about 11, 8, or 10? So guess what? Anything that doesn't have children, forget about them. Any leaves, they're not going anywhere. We're going to be bubbling down instead of bubbling up, as it turns out. OK? But if we want to, so the leaves don't even matter. OK, pop quiz. In relation to the heap size, what's the first one with no children? Nathan?
Heap size divided by 2 floor feet.
Heap size divided by 2. Floor is actually the right one, right? So the first one, and it turns out, you can check this any way you want. It turns out that if you do the heap size divided by 2 floor, you'll always get the first one that that has children, right? In this case, 12 is at position 9. 9 divided by 2 is 4.5, so it's 4. So the first one that has children is 43. So we could go just from the end of the array back and bubble down, bubble down, bubble down. Forget about that. let's just start at the one heap size divided by 2. You have instantly divided your problem in half, which is very nice. Right? Instantly divided in half because you're skipping half the nodes. Okay? Which is another interesting thing about a binary or a complete tree. Half the nodes, plus or minus 1, are going to be leaves, okay, by definition of the way a tree is built. Okay? If you take this one and you bubble it down, what's going to happen to it? 12, 12, and 43. And we're done, because it's already down at the bottom. Then we go to the next one with children, which is this one. What are we going to do with that one? Bubble it down. So it's going to switch with the 8, right? 13 and 8. And notice, even though the 8 was kind of down here, we will eventually get to it when we're bubbling down. So even though we're bubbling down, like the 8's slowly bubbling up. Right? OK, so we did that one. Let's do this one. Actually, well, it could bubble up to the top, which it will. OK, 9, what do? We bubble it down. Does it need to go anywhere? No, it's fine. Right? Nothing to do. OK, and then 14, we do that. We bubble it down. Which one does it swap with?
Wouldn't technically check left first?
Well, you might check left first, but you better compare against both children. Right? So it swaps with the one that's the higher priority. So it's going to be this way, 14 and 8. Are we done bubbling 14 down? No. Not quite yet. What's going to happen now? 11, right? 11 and 14, and we're done. Oh, let's look at a little asymptotic complexity here. OK? For each one of the we have to put them in the array first. That's going to be an n. So you're not going to get away from that n, right? And then you're basically going to, for half of them, you're going to bubble down, which is going to be kind of, it's going to be logarithmic, but it's actually, in the end, it actually ends up being a total of, I believe it's another log n. I'll have to look. But the point is, it's actually faster, especially because you chop out half the things you have to do, right? You chop out the half the things you have to do, and you end up getting a better order n log n than before, as it turns out. When you get to 160, you already did heaps in 160, right, Katie? Not listening. Katie, you already did heaps in this, right? Do you remember what the logarithmic behavior or the asymptotic behavior was for build heap? I'm pretty sure it's n log n, but it's better than the other n log n we had before, actually.
N log n
yeah.
by 2?
What's that? Yeah, divided by 2 is probably what it is, because you're only doing half.
It's just the n by 2, not the log.
Just the, well, OK. I mean,
No, the inner log, the inner n.
This one? Oh, n over 2? I guess so. Yeah, really that's going to be, yeah, OK. That's still more or less n log n, though, in the big picture. But it's actually faster. And it's faster because you're not doing every one and bubbling it up, bubbling it up, bubbling it up, bubbling it up, right? You're only doing half of them, bubbling them down. And there's no, you're not taking a bubble down that's like a huge number either, right? It could be, it's a random number in most cases. So it ends up being pretty good asymptotic complexity. OK? Wow, that's cool, though. You can insert it that way and then just go from half the tree, bubble everybody down all the way up. So it's really a for loop, right? It's a for int I equals heap size divided by 2. And by the way, in C++, remember, integers divided by 2 are a floor function. They do it automatically. They truncate automatically. Let's see. I is heap size divided by 2. I is greater than 0 because we're going all the way down. In fact, is it going to be greater than 0 or greater than 1? No, but it is going to be greater than 0 because we have to go all the way to here and then not do the next one, right? And then I minus minus. And then you're basically going to bubble down at I, right? And that's the whole thing. Okay? Pretty straightforward. Not so bad, I hope. Not so bad. OK? Yes, question here.
Does it make sense to write helper functions for bubble up or bubble down? Or would you just write it?
Yeah, it absolutely makes sense. They're not even helper functions. They're like, Yeah, I guess they would be helper functions, but yes, you should definitely write those as distinct functions, right? Because you're going to call those a lot. Yeah, good question. Good question. OK, other questions about heaps in general? No? OK, so we've got bubble up, bubble down. Those are kind of the helper functions. Those might be private functions, right? You've got insert, you've got remove, you've got min element, you've got all logarithmic behavior, you've got a nice array. See why this is like a really great data structure? It's pretty cool. You can do sorting with it. The sorting is a very fast sorting method. Probably not quite as fast as a few other ones, but it's pretty darn fast. It is. The actual overall sort is n log n to like do the overall sort, okay, which is kind of neat. We know how to do a heap sort now. Yeah, so lots of good stuff. Priority queues, right? Priority queues. OK, was it all right without the overhead projector? Yeah. Better or worse? About the same. OK, I'm hoping so, but yeah. OK, good. All right, guys. I will see you after spring break. Have a great one, and talk to you then.